Hi, my name is Sriram and today I will be teaching you this course. Object-oriented systems have emerged from several research threads. The fields of databases, programming languages, artificial intelligence and graphical user interfaces have all contributed to the emergence of object-oriented systems. The fields that have necessitated the capabilities of object-oriented systems are computer-aided engineering, computer-aided software engineering, office information systems and graphical user interfaces. Today I will be providing an overview of this course, and this course is divided into 5 modules. In module 1 I will give you an overview of the technology of object-oriented systems. In module 2 I will talk about object-oriented databases. In module 3 I will talk about object-oriented software development. Module 4 I will talk about commercial systems, and finally I will share with you how we have used object-oriented systems for developing a number of applications in our laboratory, which is called Intelligent Engineering Systems Laboratory. The overview. I will start this overview with tracing the evolution of object technology. Then I will discuss the vernacular of the object-oriented systems, that is the terminology. There are several definitions that are available in the market right now, and I will be giving you a definition, that is my definition of object-oriented systems. I will talk about classes and objects, message passing, inheritance, and finally I will summarize. First, the evolution of object-oriented technology. This particular evolution I will divide into 4 decades. First, some 60s to 70s I will call the early period. From 70s to 85s I will call the medieval era. From 85s to 90s I will call the coeval era, and from 90s onwards I will call the future. And I will place an emphasis on 3 areas, that is the input, program structure and the storage. The early period, that 60s and 70s, punch cards were used to input programs and data. To make any changes required considerable amount of labor. Many organizations hired punch card specialists whose sole task was to input programs and data on punched cards. For many of you who have used punch cards, you must have had the problem of dropping the punch cards and not numbering them. I had that problem, and it's a very painful task, as you know. In terms of the program structure, there was no notion of the separation of data and programs, and the storage, magnetic disks and tape drives were used to provide the persistence. Several research organizations at the same time were involved in the development of programming languages such as Smalltalk, Simula and a host of other object-oriented programming languages. In the second period, which is the 70s to 85s, the advent of time sharing and teletype terminals resulted in a major shift in the use of computers. Command language interfaces were used for inputting data, while line and screen editors were popular for text editing. As the size of the programs increased, the divide and conquer paradigm was used to reduce the complexity, and this was also known as procedural abstraction, where we had a main program and the main program was divided into several subprograms which called the data. And in terms of the storage, there was a need for managing large amounts of data, and this resulted in the development of database management systems. In the late 60s and early 60s, the network and hierarchical database systems were widely used. Cott's influential paper on relational database systems has brought the relational data model into prominence. Cott's primary aim was to improve productivity by providing data independence. However, the structure also makes the relational model fairly inefficient for complex information processing such as case, CAE and so on. An important outcome of Cott's work is the structured query language, or SQL, and this provided an easy means for the users to input query languages in a declarative manner. At the same time, lot of research was going on in various universities and the notion of abstract data types evolved, and in particular the work by Barbara Liskov at MIT provided pioneering work in this way. She developed the language called CLUE, and CLUE introduced the notion of abstract data types. In the 85s to 90s, Xerox PARC research on the Alto computer resulted in advanced graphical user interfaces. However, this particular work, these techniques were not utilized by Xerox and put into practice by the Macintosh computer system. In terms of the programming structure, a major trend in programming style has been the shift towards an object-centered view or the data-centered view. The object-oriented programming style implements the notion of abstract data types, which was put forward by Liskov and other researchers. And there is a direct mapping from the object-oriented programming style to the object-oriented database systems. So, we see an emergence of object-oriented database systems in areas such as engineering and office information systems. However, you must note that there is still a lot of relational bases developed out there, and these systems continue to dominate, but I see an emergence of the object-oriented database systems. What about the future? Where are we going in the future? The future, in terms of the input, we will see, and in addition to the graphical user interfaces, things such as voice, vision, and natural language communication modes may become very popular. Object-oriented programming styles will be dominating the programming landscape, and in terms of the databases, we might see a mixture or a hybrid of relational databases and object-oriented databases emerging as the prominent role. Now, I will talk about some basic concepts of object-oriented systems. Especially, I will focus on the vernacular of object-oriented systems. The vernacular. There are 4 basic mechanisms for any that a system should have to claim to be object-oriented, and these 4 mechanisms are defining objects, forming taxonomies, sending messages and methods between objects, and implementing inheritance or allowing inheritance process. Associated with these key basic mechanisms, we also have certain key concepts such as overloading, abstraction, polymorphism, dynamic binding, encapsulation, and persistence. As we are talking about these basic mechanisms, in the same time we will be talking about the key concepts. So, from time to time I will be giving definitions of what these key concepts are. There are a number of related terms which are used in other fields such as artificial intelligence and graphical interfaces. These terms are frames are used quite a lot in the AI area. The term called widget is used in the user interface area, and we also see things such as events, triggers, signatures, and agents in the artificial intelligence area. First, let me talk about what an object is. Objects combine data and procedures. That means objects have both structure, state, and behavior. Objects respond to messages, and objects have unique identities. Now, these are the 3 characteristics of an object. There is a small cartoon here which shows the nature of objects. Here is a person who says he is from Bank of Credit and Commerce Incorporated. This is a particular object which is sending a message to another object who is a salesman. This object, the minute he receives a message saying that I am from BCC, immediately responds with another message, how about buying some Acme bonds, which are junk bonds. So, to summarize about objects, objects have structure, behavior, and identity, where the structure encompasses all of the properties of the object plus the current dynamic values of each of these properties. And the behavior tells you how an object acts and reacts in terms of the structural changes and message passing. Identity is that property of an object which distinguishes itself from other properties or other objects. So, let us look at some typical objects. Here are some typical objects that I am going to illustrate the concepts of object oriented programming using these objects. The first object here is Mary's car. It is a unique object. Then we have Ram's car, we have Jack's car, we have Red's truck, we have John's truck, and we have Hussein's truck. Let us have a closer look at Mary's car. In terms of the structure, we can define Mary's car as shown in this particular slide. Mary, there is a owner and the owner is Mary. The model name is Benz. The manufacturer is Daimler-Benz. It has an ID and the ID is the vehicle ID. For the purposes of this talk, I am using 999. There is a model year which is 1989. The exterior color is red. The interior color is brown. The cost of this car is $40,000. There are a number of components that constitutes this car: body, drivetrain. We will come back to this subparts later on. And this constitutes the structure of this Mary's car. And what about the behavior? Well, there are several things we can do with this structure. How do you access the elements of Mary's car? One way to do it is to make all the attributes public, and the other way to do is to provide an interface to get into this particular structure. And here is the interface that we provide. To get the model name, we cannot get it directly, but rather we use we can use an interface where you send a message to Mary's car, get model name, and associated with that model name there is a procedure which gets activated, and we will come to that in a minute. Similarly, to get the ID, we have a message that we send to Mary's car, get ID, and there is a procedure called get ID which gets invoked. And I have also introduced another behavior here called diagnose, and this behavior will tell you how to diagnose problems with Mary's car. So, now we have the structure and then we have the behavior. The structural aspects here are define the overall physical structure of this car, and the behavior will tell you how to get values from the structure. In addition to that, it also does things like diagnose and a number of other things that can be added here. Note that in this particular slide, I have added something called private and public. What this means is that this particular private part is hidden from the public interface. So, to get any values from the private part, one has to go through this public interface. So, this is said to be encapsulated, and we will come to that in a minute or so. Now, let us have a look at the behavior aspects of Mary's car. So, the way it works is the following. You send a message get ID to Mary's car, and there is a procedure called procedure get ID which gets invoked, and that procedure will do something and go and get the ID. Imagine if someone were to ask your salary, for example. It all depends who asks you for your salary. If the IRS asks, you give one answer, and if someone who is a potential employer asks you a question, you give another answer. So, depending on who asks you the salary, you give a particular response. So, that particular behavior now can be encoded using procedures of this sort. So, you can hide the internal details of the implementation from the external interface as such. There is another thing we can do with this car with Mary's car is to send a message called diagnose. When you send a message called diagnose to Mary's car, what happens is a procedure called diagnose Benz will get invoked. Now, this procedure is not an ordinary procedure, but this procedure is a knowledge based expert system. Now, look at what we can do now. We can add artificial intelligence or intelligence, some kind of an intelligent behavior along with a particular object, and this intelligent behavior can be encoded in knowledge based expert systems, where knowledge based expert systems are computer programs which incorporate human expertise. Typically, these systems contain the following components: a knowledge base where you have knowledge encoded either in rules are facts or objects. A context mechanism, which can be viewed as a short term memory, where you have the current working aspects in the short term memory. Sometimes this is also called working memory. And then we have an inference mechanism, which actually is the problem solving strategy. So, let us have a look at the knowledge base and how we can encode rules. These knowledge bases offer you a flexible way of encoding human expertise. Here are some rules for diagnosing Mary's car. The first rule says, if problem equals dead battery or problem equals bad ignition system, then you have found that the particular problem with that car. How do you find whether the problem is dead battery? We can write another rule which says, if the init problem, that is the initial problem, is starting system and headlights are dim or dead, then the problem equals dead battery. And how do you determine whether the problem is with the init starting system? We can determine it in the using the following rule. If the ignition key is on and the engine state is not turning over, then the init problem is equivalent to starting system. Now, assuming that our knowledge base has these three rules. Now, however, we can add, suppose we find a new problem with the car, we can add in very easily, as is shown in this particular slide. We are adding a problem equals bad starter, and then we add another rule into this process, where if init problem equals starting system and the headlights equals on, then the problem equals bad starter. So, using the knowledge based framework, what we can do is incrementally add knowledge to the system. So, we have objects have behavior, and the behavior can be encoded as a knowledge based expert system. In the knowledge based expert system, we can encode rules like this, and in addition to that, we can also add several inference mechanisms such as forward chaining, backward chaining, hierarchical refinement, constraint handling, qualitative reasoning, case based reasoning, neural processing, and a host of other things. If you want to know more about knowledge based expert systems, there are a number of texts available, including the one that we are putting out from our laboratory, and if any one of you is interested, please feel free to give me a call on that. So, to summarize so far, what we have done is, we have taken Mary's car and defined a structure to Mary's car and a behavior to Mary's car, and we said that we can have several kinds of behavior. One kind of behavior to access into the elements of Mary's car, and the second kind of behavior which will provide us things such as diagnosis, maybe design, and a number of aspects of Mary's car. Now, associated with for separating this private and public interfaces, we have the notion of encapsulation. What is encapsulation? I can show you encapsulation with the following slide, where now we have the public interface here shown outside in this cell, in this capsule, and then we have internals, which would show the attributes. Now, the internals here are, for example, the ID, which is 999, and model name, which is Benz. So, the only way Oz can get into the model name is to get the model name is send a message called get model name to Mary's car, and when Oz sends the message get model name to Mary car, this get model name will go and get the model name for Ben's car. So, it's called encapsulation because you are encapsulating information here, and the only way you can get into this information is through this public interface. It is like a capsule, like a Tylenol capsule or some capsule like that, where you don't know what the internal details are. The only way you can get to the internals or the innards is through this public interface. So, the innards are hidden from the public as such. However, if you look at Mary's car, it's kind of obvious that we don't really need to hide model name as such, because model name we can easily see from looking at Mary's car. So, what we can do is, we can take this particular model name out from the structure, from the private part, and put it into the public part. And similarly, what we have done here is to add in a new behavior into the private part, and that this particular behavior you don't want everyone to see. So, from some public interface, I can go into this private behavior as such. So, now what we have done is we have divided Mary's car into a private part and a public part, and in the public part we have both structure and behavior, in the private part we have both structure and behavior. So, the structure and behavior now can be encoded in both the public part and the private part. There are several variations of this process of encapsulation, and I will give you one variation. The one variation I showed you just now is this one, where now Oz can go and get the model name directly from Mary's car without sending a message. Now, the only disadvantage of this is, now if these variables are public, anyone can access these variables. It is something like my lawn, for example. The reason I mow my lawn is that it is a public variable, and people see my lawn all the time. They not only see my lawn, but they also modify my lawn by dropping in various elements which I do not want to be dropped on my lawn. So, the lawn is a public variable. On the other hand, the things in my house, such as my living room, my bedroom, and if someone wants to know what furniture that I have in these rooms, they have to ask me. They can't just come in, and they cannot have a public interface to that. So, the public variables are public to everyone, and you can make changes. So, there is a danger to that, and the private variables are private, and the only way to get into the private variables is through the public interface. Some languages such as C++ offer a kind of a variation for this encapsulation. There is another variation where you have the private part, a protected part, and then a public part. And we will see when we talk about C++ in module 4, we will see how this thing is implemented in that particular language. C++ is one of the popular object oriented programming languages, and we will come back to that in module 4. Let us now look at Jack's car. In a similar way, just like as we have defined Mary's car, we can now do the same thing to Jack's car. Now, look at Jack's car. Jack's car is very similar to Mary's car. The owner is Jack, the ID is different, 949. The model year is almost the same. The interior color is a little different. The cost is about $2,000 more. Jack has some additions onto it. Otherwise, things are the same in the public interface and private interface. So, what we have seen here is some common elements between Jack's car and Mary's car. So, what do you do with that? Here is what we do. That is the next part we will discuss. That is the classes and instances. So, what we can do now is to take Mary's car and Jack's car and abstract out the common information and form a new car called Ben's car. And here is an example of Ben's car. So, we have taken the abstract properties and the behavior here, and we have taken the common elements and placed them in the Ben's car. So, here we have owner, the ID, model year, interior color, the picture, which now we have added a new element here called picture, which can point to a Ben's car dot picture. Now, we can show picture on the screen too. In terms of the public interface, the model name is Benz, the manufacturer is Dalmar Benz, and what we have done is we have given it a default value called black. So, in case if you get information from the Benz car, we will get if you ask for the exterior color, we will get the answer as black. Interior color, we have left it open, and then we have added in a new behavior element here, which is to design Ben's car. I am doing this process in a bottom up manner. I can probably do it in a top down manner too. Okay, now let us look at Mary's car. What we do now is to define Mary's car as an instance of Ben's car. Mary's car, we do not copy all the things which are in Ben's car, but only those parts that are to be modified in Mary's car. The things that need to be modified are the instance of which is the same Ben's car. The owner is Mary, ID is 999, model year we have changed to 1989, the interior color is brown, the cost is different. The components are the same, but the subparts in Mary's car are different than the subcar parts in other cars such as Jack's car. So, we have modified that, and the exterior color is red, as we have seen before. In a similar manner, I am going to define Jack's car. Now, Jack's car is an instance of Ben's car, and some of the attributes have changed values, such as exterior color. Other attributes, there are no changes, so we do not need to make any changes in Jack's car as such. So, let us look at the taxonomy of the cars as such, which was shown in the previous figure. So, we have Hussein car, which is an instance of the BMW car, Jack car, which is an instance of Ben's car, Mary car, which is an instance of Ben's car, Ram car, which is an instance of Toyota car. So, we are defining two new terms here. One term that I am going to define is an individual object. Individual objects are objects which cannot be further classified as such, or which cannot be further instantiated. Again, this is a definition which I am giving. This is my view of what the individual object is. Now, these individual objects are grouped into what are known as class objects through this relationship called the instance of relationship. So, the instance of relationship links individual objects to the class objects. So, we can take several individual objects and then group them into a class object through the instance of relationship. So, this aspect going from the individual objects to the class object is a process which is called classification, and the relationship classification is denoted by the instance of link. Then we can take these class objects such as the BMW car, the Benz car, and the Toyota car, and we can group these class objects into another class object called a car, because they are all cars, as we know. And that relationship, that the relationship that links these class objects into another class object, which is the car object, is called generalization. So, now we have I have introduced two types of relationships, the generalization relationship and the classification relationship. The classification relationship maps the individual objects into the class objects, and the generalization relationship generalizes the class objects into another class object. The generalization relationship is generally given by ISA term. Now, the process going from here to here is called specializations. From the super element class, which is the car, to its subclasses is called specializations. Similarly, going from the class to the individual objects is called individualization. So, we have classification in this direction, we have generalization in this direction, we have specialization in this direction, we have individualization in this direction. This relationship between individual objects and the class objects is denoted by the instance of link. The relationship between the class objects and another class object is denoted by the ISA link. In some languages, the ISA link is also called super and AKO, and several other terms are used for that. But I will be using throughout ISA to denote the generalization concept and instance of to denote the classification concept. Now, the class car now is a vehicle. The vehicle now is a more, we'll come to vehicle soon and see how the vehicle looks like. We have all the elements which are common to all the cars, if you go back to the previous slide, like the BMW car, the Benz car, and the Toyota car, we abstracted it into the car level. Okay, now you might ask a question, why is that I don't see those particular attributes around here? And I have also made one more change here. If I go back, that is between the Benz car and the class car. If you look at this particular behavior, you see that it's now called diagnosed car and not diagnosed Benz car. This is particular. So, this is peculiar to class car itself. Well, to clarify that, let us have a look at the vehicle taxonomy. If you look at the vehicle taxonomy now you can see that the cars, trucks are grouped into the super class, which is the vehicle given by this ISA link. So, we can now create these kinds of taxonomies for objects in other domains too. So, let us have a look at the class vehicle, which is the structure, and then let us have a look at the behavior later on. So, the structure kind of looks like this, which is similar to the structure of car, which is similar to the structure of Brain's car. We have owner, ID, model year, interior color, cost, picture, components, subparts, and then we have some behavior encoded here. So, the private part of this particular vehicle contains both structure and behavior. Then we can now, as we have done in the previous slide here, the class car is defined is a vehicle. So, what happens is that this particular class car inherits all the information from this vehicle. I am describing this in English like terms right now, and as we go further in the day, I will also tell you how these concepts are implemented in languages such as C++ and in database systems such as object store. The public interface is shown as follows. We divide the public interface of the vehicle into several areas, the structure and the behavior now can be grouped into access behavior, problem solving behavior and display behavior. The access behavior here is shown by these terms get ID, get owner. The problem solving behavior is shown by diagnose and design, and the display behavior is shown by this display, and we can keep incrementally keep adding more and more behavior or more and more attributes as we refine these things further. What we have introduced here is a key term called abstraction, where abstraction involves concentrating only on the essential structure and behavior and leaving the details further. So, what we could have done is we could have defined the abstract class called vehicle, and then we could have put in more and more detail as we go into the class car and Ben's car and Mary's car. So, as we are going down the hierarchy, we are adding in further detail. So, this process is called abstraction. As I have promised before, I will be kind of talking about the key concepts as I am talking along the same terms here. So, what I have done so far is to introduce two key concepts, abstraction and encapsulation, and now I will be introducing the other key concepts. The next thing I would like to talk about are messages and methods, because objects, as we have seen, respond to messages, and we have given you an example before how a particular object responds to particular messages. So, we also shown in the vehicle class how we can group these messages into various protocols like the access protocol and the display protocol. Now, the object oriented systems support a concept called polymorphism, where the same message sent to objects at different objects will invoke different responses. So, now we are introducing a new term called polymorphism. For example, in this particular case, if I send a message called diagnose to vehicle, I would invoke the procedure called diagnose vehicle, as we have seen before, and if I send a message called diagnose to Ben's car, a procedure called diagnose Ben's car will be invoked, and these two things have different behaviors as such. So, the same message sent to different objects invoke different kinds of behaviors, and this is called polymorphism. So, to summarize, polymorphism is a feature by means of which data and methods assume dynamically various forms during run times. The next aspect, and a very important aspect of this process, is the inheritance process. So, in the vernacular, we have defined the basic mechanism, we are discussing the basic mechanisms, and then I have said there are 4 types of basic mechanisms that have to be in any object oriented language: defining object, forming taxonomies, sending messages, and finally defining inheritance. Inheritance is an extremely powerful idea where classes and instances inherit both behavior and structure. Inheritance supports sharing, overriding, and specialization. We all inherit certain characteristics from our parents. We inherit structure, we inherit behavior. Often many people, depending on which side of the family they are, they will tell you, you resemble your father or mother. Now, what does this mean? This means that you structurally you kind of look like that. Similarly, they might even say that you walk like your dad or you walk like your mother, you talk like your dad or you talk like your mother. So, this process is called inheritance, and we will discuss this process through an example. So, the elegance of object oriented programming or object oriented systems is that it kind of tries to replicate the way we are in the nature. So, let us have a look at the structural inheritance. I can give some default values to vehicles. I can say that most vehicles cost $15,000. Most vehicles, the exterior color is brown, and the components, the vehicles have a body, a drivetrain, and so on. Now, I have defined the class car as a subclass of the class vehicle. And when I ask here what is the exterior color, the answer I will get back from this object is brown, because this information, remember, is not in this particular object. However, the information exists in a higher level object. So, the information from the higher level object is now inherited to this lower level object. On the other hand, if I ask what is the cost, I get $10,000. That means what I have done is inherited structure, and then I overrode the structural behavior. In a similar way, for example, you can inherit certain features from your parents which you may not like. Like for example, you might inherit a long nose or a short nose. You might want to cut the long nose into a short nose, make it medium, and you want to elongate the short nose by a means of called plastic surgery. So, this is very similar to this process where you inherit certain structural attributes and values of these attributes, and you change the values of these attributes. Note that in addition to inheriting all these attributes, you can change not only the values, you can also add in new attributes anywhere down the taxonomy. I have a triangle here. I will tell you what the triangle is later on. When we come and talk about object oriented software development. For the time being, just understand that this one denotes the subclass relationship. Now, if you take the Benz car is a car, but however, I have changed now the exterior color to black. So, if I ask the exterior color here, I get the answer black. If I ask the exterior color here, I get the answer brown, because I have inherited brown from here. I have inherited brown from here, but I overrode the brown and made it black. Similarly, I took the cost and changed the cost to $40,000 as such. However, in the Toyota car's case, if I ask the cost, I get $10,000, and if I ask the exterior color, I get the answer brown, because this brown is inherited through this link here. Now, I make Mary's car, which is Mary's car an instance of the Benz car, and I only change the exterior color to red. So, the cost remains the same, which is $40,000, and the exterior color is now changed to from black to red. If I have Jack's car here, remember Jack's car, the cost is $42,000. So, I override that particular structure here. Please note that I'm only describing here single inheritance, and there is something called multiple inheritance, where you can inherit structure from two parents instead of one parent, just like we inherit certain features from our father, from our father side of the family, and certain features from our mother side of the family. Similarly, here we can do the same thing. And in terms of the behavioral inheritance, we can do the same process as such, where in this case the way we have I'm only showing you the behavior and not the structure here. I have two behaviors here, get ID and diagnose. So, if I send a message to vehicle called get ID, I invoke procedure get ID. If I send a message called diagnose here, I invoke the procedure diagnose vehicle, and this is a knowledge based expert system which knows how to diagnose vehicles. Take for example car. Now diagnosing cars are very similar to diagnosing vehicles, except that there may be some subtle changes. So the diagnosis of a car is little different than diagnosis of a vehicle. So I define a new procedure here, but the message selector is the same. This is called generally message selector in object oriented programming, and when I send the message diagnose here, the procedure that gets invoked here is diagnose car. I can go further down, and for Ben's car, if I send a message called diagnose, I have a procedure called diagnose Benz, which is very similar to diagnose car with some so diagnose Benz is very similar to diagnose car with certain changes in here. Similarly, for diagnosing Toyota car, very similar to car diagnosis, except that diagnosing Toyota car has certain subtleties which are not the same for all cars. Okay. One thing you need to note in here is that this is how we have implemented the polymorphism process, where if you send a message called diagnosis here, the procedure diagnose vehicle gets invoked, and then when you send a message Ben's car, the procedure diagnose Benz gets invoked. Now we are now inheriting the behavior along these lines, and we are also overriding this behavior at various classes. Mary's car is an individual object, and we are not changing the behavior here, but we can also change behavior at this level. But in many cases, in some languages allow this and some languages don't allow it. Languages such as Lisp are fairly flexible and they allow changes at this level. Languages such as C++ do not generally allow changes at this level unless you do something to C++, and we will talk about how to do that later on. Now here, when we talked about overriding behavior, we didn't mention one thing. That is, what you can do is you can take the behavior that is present in the parent's class and you can reuse the behavior. This is the process of sharing behavior. For example, there are a number of books which they sell in the market called Car Repair for Dummies. Okay. Now this Car Repair for Dummies book may not be suitable for all cars, or it may be only suitable, there may be some generic procedures involved in there. So you can buy the book and know in general how to repair a car, but you may not know the details as such for different cars. For example, you have to buy, if you have a Toyota car, you might want to buy a particular manual that is sold by Toyota people, which have some similarities to the diagnosis of cars in general, but there's some peculiarities to Toyota car as such. So the way this is implemented is through this process called behavior sharing, where now if I send a message called diagnose to car, the procedure diagnose gets invoked, and the procedure diagnose is a knowledge based expert system, except that it is divided into several areas where I can have car specific rules, and there are rules which are common to the to cars, trucks and so on, which are in the vehicle case, which are these rules are encoded in the vehicle class. So the way I do it is I first write my car specific rules either here or here, but then I also send a message to the parent to invoke the parent's diagnose vehicle in this case, where I send a message called send super, and when I do that, when I use this keyword called send super and I send the message called diagnose, it will go and pick up the appropriate parent in this taxonomy and invokes the appropriate procedure in there. So what I am doing now is I am reusing certain behavior which is defined at the parent level and in the child level, and we can continue this process along in this case. Now I will define another concept called dynamic binding. Now this dynamic binding is a process of attaching a variable name to an object type or a message selector to a method. We have seen in the previous example polymorphism, where if you send a message diagnose to the vehicle car, the procedure diagnose gets invoked. When we send a message diagnose to Ben's car, the procedure diagnose Benz gets invoked. Now, during runtime, what is happening is, depending on where I send the message diagnose, the appropriate procedure gets bound to this particular message. Here, this particular message, this particular method gets bound to this particular message. Here, this particular method gets bound to this particular message. So, the binding process is attached. In this case, we are attaching the method to an appropriate message selector. In the vehicle case, we attached procedure diagnose vehicle to diagnose, and in the Benz car case, we attached procedure diagnose Benz car to diagnose. So, that means this associating a method to a message selector is done during runtime, depending on depending on which object or which class that we sent this particular message to. Now, there is another thing that we have not mentioned here, is also is attaching a variable name, attaching an appropriate object type to a variable name. So, the variable name and the object type are kind of bound in some way to one another. Now, some languages such as C++ do not allow this for attributes. They do allow it for their methods, but not to the attributes. On the other hand, some languages such as Lisp allow this process, where you can determine the type of the attribute during runtime. So, in other words, in languages such as C++, you cannot determine the type during runtime, and the type has to be determined during compile time. So, they do not allow dynamic binding of attributes. However, they allow dynamic binding of messages to methods. In languages such as Lisp based languages, things are a little different, where you can bind the variable to a particular type during runtime. This is a very useful process for doing prototyping, but it may not be that useful if you are developing large scale software development as such, because the types are not known at the compile time, but they are known at the runtime. A related concept to this dynamic binding is this process of overloading. We have not discussed overloading so far, but what in some languages the operators could be overloaded. That means, if you have for example, you might have an operator like plus. Now, plus takes two arguments here on either side, let us say 5 plus 4. On the other hand, I want to 5 is a particular object. If we, in object oriented systems, everything is treated as an object. 5 is a particular object of the type integer, 4 is a particular object of the type integer. Now, this plus operator is taking two objects of different types, that is 5 and 4, and it will return 9 to you. Now, however, what happens if I do A plus B, where A is a matrix and B is a matrix? What you can do in many object oriented languages is to overload this plus operator. So, you can the operator can be used for both matrices and integers. That means, the operator can take A plus B, where the operator can take A and B as arguments, as operands, where A could be either a matrix, or A could be either an integer, or A could be anything in the world. A could be even a string. So, I can have A as a string, B as a string, but still if I write A plus B, that operator knows what its operands are, and so it acts appropriately, and this process is called operator overloading. So, now we are going to summarize some of the concepts that we have learned. Object oriented programming organizes programs by combining data, which is structure, and procedures, which is behavior. It causes actions through message passing, and we can obtain sharing through the process of inheritance and object oriented programming can be integrated with other paradigms. We did not talk about object oriented database systems, which we will be talking about soon in the next module, and object oriented database systems extend object oriented programming languages. As we were discussing, there are 4 mechanisms of object oriented systems or object oriented programming, that is defining objects, forming taxonomies, sending messages to various objects and invoking appropriate methods, and sharing code through this process of inheritance. And we also defined, along as we were talking about these basic mechanisms, we also talked about several key concepts. And the key concepts that we talked about are abstraction, where we only describe the skeletal structure and behavior and differ the details to a further state. And the next thing we talked about is polymorphism. Poly is many, morphism is forms, where the object can take multiple forms during runtime. And we have seen some examples of that, that is objects kind of respond to different objects respond to the same message in different ways depending on the particular state of the object at that particular time. We also talked about encapsulation, where the innards are hidden from the exterior, or we have a clear division between the private part of the object and the public interface to that particular object. So, the innards are hidden from the outside world, and this process is called encapsulation. We talked about overloading, which is a kind of a polymorphism where both operators and functions are overloaded. So, where is the future for object oriented systems? There are 3 areas which I think the future lies in, and the 3 areas for the future of this object oriented systems are: 1, software factories; 2, collaborative work; and 3, multimedia. Let's take a few minutes and discuss about each one of them. Software factories. You have seen these objects kind of encapsulate both structure and behavior. So, what we can see in the future is just like as we buy parts for cars, similarly we will go and buy software objects. Brad Cox, in his book on object oriented programming, talks about software ICs. A software IC is very similar to the integrated chip that you see on your printed circuit on your boards in your computers. It's just an independent unit, it's a unit where you can go and plug in an appropriate part of your program. I think this trend will play a big role in the future. However, one problem I see is the management of these software ICs in terms of how you are going to get your royalties for your particular software, because there is a difference between hardware and software. For example, the parts, they consume certain resources, they consume certain material, whereas software, in terms of the cost involved in the materials, is kind of negligible as such. The only thing you do is to sell it on floppy disks or maybe some other medium, optical disks, and these are not very expensive items. So, it's going to be an extremely hard thing to manage the software ICs, but however, I think the way we are going in the future, we will see that there will be some way of managing software ICs. So, where people will sell you, just like they sell you printed circuit boards, they will sell you skeletal programs, and you can go and buy a software IC and place them in the appropriate part. It's a little bit of a controversial topic, but it's an interesting topic. The second area is collaborative work. Our ability to compete in the global markets will depend on how well we collaborate in the future. In fact, in the future, I think this particular broadcast will be done in a very different manner via the computers. So, there is a big trend towards computer supported collaborative work, and I believe object oriented systems are going to play a major role in this process. We will, in module 5, show how we have implemented things for concurrent engineering or computer supported collaborative engineering by using by extensively using some of the concepts that I will be presenting in the next 3 modules. Finally, multimedia. We are seeing this trend already in terms of Apple Macintoshes, IBM PCs, DEC machines, and so on, where there is a trend towards selling machines which incorporate or facilitate voice, video, and sending pictures and all kinds of things. So, the trend towards multimedia systems is there, and then we will see this over and over again in various systems in both computers in terms of hardware and software. At MIT, in fact, we have a major program at our Center for Educational Computing Initiative, where we are developing state-of-the-art multimedia system using object-oriented technologies. That concludes module 1, and in the next module I will talk about object-oriented database systems. In object-oriented database systems, I will elaborate on the concept of persistence and show how object-oriented programs can be easily mapped onto the physical databases. We will take some examples from engineering, and then I will show you how this particular technology is very useful for solving a wide range of engineering problems. Thank you, and we will see you in module 2.